How are you?
I'm doing good, Professor.
So today I wanted us to record one last video for this class, but maybe we should break it in two parts.
Okay.
So both of them are related to the Riemann Zeta-Function. The first part, let's say, due to Dirichlet. Maybe we should look at the screen first.
Okay.
If we, okay, Dirichlet, so our video on the Riemann zeta function. So maybe we start with the, if we recall, definition of the Riemann zeta function, that series. It was, you denote it by Z. So capital Z of S is equal to 1 plus 1 over 2 to 1 plus 1 over 2 to the S plus 1 over 3 to the S plus 1 over 4 to the S and plus data. Now, that's an example of a Dirichlet series. So what's called a Dirichlet series is a sum that looks like this. It has these numbers as denominators. So 2 to the S, of course, a 1. The denominator of the first one is 1. But then a 2 to the S, 3 to the S, 4 to the S, and so on. But the numerators are not necessarily equal to 1. Some other numbers. We take any numbers that we want, we put them there, and that's a Dirichlet series. Now, as an example of a Dirichlet series, that was considered by Dirichlet, for instance, is the following. Let's call it capital L of S. And let's take only odd numbers, but with alternating signs. So 1 minus 1 over 3 to the S plus 1 over 5 to the S minus 1 over 7 to the S and so on. Now, just as Z of S, L of S is also convergent as a series for all S larger than 1. But unlike the case of the Riemann zeta function, something different happens now when we let S approach 1, S decrease. So let's write this as a statement or a remark. As approaches 1, L of S approaches, and now the difference is that it doesn't approach infinity as in the other case. Approaches concrete real number, and it's the following. We can write it as a series, because if S approaches 1, then 1 over 3 to the S approaches 1 over 3 to the 1, so 1 over 3. 1 over 5 to the S approaches 1 over 5, and so on. So this approaches 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, and so on. Now the sum is not infinite. This is a convergent series. We can write it's convergent series because it's an alternating series, and we learn in calculus that such a series will converge. A series that looks like this. We can actually find the sum. And just before we start the recording, I ask you to write a quick program to compute this. It doesn't converge quickly. It converges slowly, but it converges slowly to some number like 0.7 something. Oh, and you did compute.
Do you stop?
Oh, yeah. It's an example. There's like 0.7 something. Well, the reason I wanted us to compute this, so we see that this number, it's not infinite, it's just a real number, and it's not 0 either. Because what I wanted to do is, again, to take a logarithm of this a bit later, in a few minutes. But let's investigate this a little bit more. It should not look familiar, this number. But if we multiply it by 4, This should be familiar. So if you can just multiply by 4 this series, so these are probably the same numbers, but all of them are multiplied by 4. So now we see where this is going. It's going to, I can't see very well, but it's 3.1.
3.15, 3.132.
Okay, right. And if we take more and more terms, we will see that this approaches pi. So we can say that the sum of the series is pi over 4. So we can write this. All right, pi over 4. Now let's prove this. First, as a side comment, let's say nothing to do with the Riemann Zeta-Function, but let's prove this. So this is actually L of 1. So you see, zeta of 1, it's not defined. We can talk about the zeta of 1, but this function L of 1 is equal to pi over 4. We can say equals pi over 4. Well, let's prove that that sum is the Deviant series converges to pi over 4. How we do this? We recall our last video, Achilles. Not Achilles, just the Achilles identity, let's say. It looked like this. It was 1 plus x, or our generalization of that. 1 plus x squared. Let's write a few terms. X squared, x cubed, and dot, dot, dot. This was equal to 1 over, and the denominator was 1 minus x. Now this holds for this holds true for x between -1 and 1, strictly. Now let us do the following. Let's say let x equals minus t squared. Minus t squared, comma, where, let's see, something about t. It's -1 strictly less than, -1 strictly less than t, -1 less than t, and strictly less than 1. Before going any further, I want to see what x, what can I say about this x. Now, if t is between -1 and 1, t squared, it's positive or 0, but it's less than 1, t squared. So minus t squared is between -1 and 0. I just wanted to make sure that our x, that's minus t squared, is in the proper interval, so we can substitute, we can use it. So indeed, yes, and this is less than or equal to 0. It can be 0 when t is 0, because t was allowed to be less than or equal to 0. Okay.
And also less than or equal to -1?
Yeah, and no, strictly
No.
larger than
Yes.
-1, because t was strictly larger than -1, but strictly less than 1.
Less than,
so
okay.
it's going to be less than 1. Okay, so we are allowed to use this minus t squared in our formula for say Achilles identity, so to speak. What we get? Let's replace x by minus t squared in that equality, and I get 1 minus t squared. But then the next one is plus t to the 4, and then the next one is minus t to the 6, plus t to the 8, and so on. Exponents are even numbers. And this is equal to now 1 over, and let's see what happens in the denominator. It's 1 plus t squared. Yeah, plus t squared, because x was minus t, yes. And this holds for, let's recall, for all t between -1 and 1, for -1 less than t less than 1. Yes, -1 still less than t less than 1. Now, as we did last time with an identity, we proceed in the same way. We want to find two functions of t this time, whose derivatives are the two sides. So on the left side, it's clear. We write it as a series. Let's see. The derivative of t is 1, yes. derivative of what is t squared? You know, t cubed divided by 3. Yes. And then, yes, t cubed is this quantity divided by 3. And then plus t to the 5 over 5. Then minus is alternating t to the 7 over 7. And so on. We also know from last time that this is not necessarily equal to the function we find on the right side. But if we add a constant, will be. So maybe we put a constant at the beginning. C plus this will be equal to. Now, do you know a function whose derivative is a function of t?
Yes.
Oh, what function? Right. That's all right. But there's the inverse tangent. Let's say r tangent.
Yes.
Let's write it as r. Yes, r tangent of t. Now, again, next step is to find a constant.
Yes.
To find a constant, we need to just let t equals something that is allowed, something that's in the interval. T equals 0, easiest. T equals 0. And then on the left side, everything vanishes except for the constant. Mm-hmm. On the right side, we get r tangent of 0, and that's 0, right? Because the angle whose tangent is 0. C equals 0. So now that we know that C is 0, we can remove it from there and get an identity. All right. Now, we have this identity in the same interval. That's the open interval minus 1, 1. But let's see what happens when we let t approach 1. So we say in words, let t approach 1. And we obtain, on the left side, you see, right. You started with the right side, but you can write on the left side first. It's exactly 1 minus 1 over 3 because t approaches 1, t cubed will approach 1. So it's 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 and so on. It's exactly our series before. And this now is equal to r tangent of 1. Let's write this, r tangent of 1. And let's see if we recall what that is.
Pi by 4.
Yes. All right. Because even if we recall definition of arctangent, is the angle whose tangent is 1. But an angle for which, and the tangent was, if you recall, is right triangle is that side divided by this side. If they are equal, so that the ratio is 1, it means that we have an isosceles right triangle. So the angle is 45 degrees. In other words, in radians, as we work with, is pi over 4. Good. So that's an explanation for why that value L of 1 is well defined. It's pi over 4. It's not 0. Now, if we take a logarithm of that, so then we have natural log of L of 1. Okay, well, let's do the following. Let's say log of L of S, ln of L of S approaches natural log of pi over 4 as approaches 1. Now, to make a long story short, if we look at this series L of S, this series also has an Euler product. And again, we can use those logarithms of the product. I mean, the logarithm of L of S will be a logarithm of the product, which again will be the sum of the logarithms, which again will be close to exactly 1 over 2 to the s plus 1 over 3 to the s plus 1 over 5 to the s and so on. So let's say this is close to right, 1 over, let's say, 2 to the s plus 1 over 3 to the s plus 1 over 5 to the s. Just the sum of inverses of primes. Yeah, we can put 3 to the s plus 1 over 5 to the s plus blah, blah. Okay, but that's not quite correct. You see, in our series L of s, we avoided all the denominators that are even numbers.
Yes.
There's no 2 to the s, no 4 to the s, no multiples of 2. And for this reason, 1 over 2 to the s will not be there. So we can remove this 1 over 2 to the s. Yes. We only have 1 over 3 to the s, 1 over 5 to the s, 1 over 7 to the s, and so on. Now, if that is close to this, and ln of s converges to that number that, or approaches that number, that's not infinity. It shows that when we take s to go to 1, we get a series that is convergent. So the series when we replace s by 1 in the just the last line here. So replacing s by 1, we obtain a series that converges. All right. I said to make a long story short, but just to give the ideas. But what is the series when we replace this by 1? It's 1 over 3 plus 1 over 5 plus 1 over 7. Let's write it. So let's write another line, just the numbers. 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over 11 plus that. Just the sum of inverses of primes converges. I'm waiting for complaints.
This is a divergent series.
Of course it is. That's what we proved last time. That's a divergent series. Now we only remove one term. That's 1 over 2.
Yes.
Okay. So something is not right. But on the other hand,
minus plus.
You see, our series was not 1 over 1 plus 1 over 3 to the s plus 1 over 5 to the s plus 1 over 9 to the s. If we put pluses all the time, then we get to this. But then we'll still be divergent. But we took an alternating series. Yes. Plus, minus, plus, minus, plus, minus. And then what we get here is a series that doesn't have these signs are not all the time plus. But it's not also true that it's plus, minus, plus, minus, plus, minus. Let's have a look at our series L of s and see what happens with our prime numbers in the series. Let's go back. Yes, because some of the primes appear with a minus in front of them. Okay, let's look at L of s above, where we define L of s today. No, the first thing we did today, L of s. You see, second line. You see, in Z of s, we had this 1 over 2 to the s, of course, which we don't have in L of s. But then we also had 1 over 3 to the s, and 3 appears with a plus. Now something changed. This prime number 3 to the s appears with a minus in front. And when we work with those logarithms, I said, to make a long story short, we won't do this. Oh, by the way, we'll do this properly and in much more detail in our 531 class this whole semester. But just to have an idea what is happening here. Which prime numbers in L of s appear with a plus, and which prime numbers appear with a minus? You see, 3 appears with a minus sign in front of it. 5 appears with a plus. 7 appears with a minus. How about 11?
Minus.
A minus. Even if it's the next prime after 7. It doesn't matter. It still has a minus. And that will translate, when we do this computation with the logarithms, in our sum that we established as convergent. It's not that sum. So there was the contradiction. It's not that sum. It's still convergent, but it's not that sum. So let's go there. And and replace. So let's remove the word contradiction. Let's keep converges that it converges, but let's put proper signs. So it's minus 1 over 3 in front, plus 1 over 5, minus 1 over 7, minus 1 over 11. Aha! So we know which primes appear with a plus, which appear with a minus in front.
1 mod 4 and minus 1 mod 4.
Exactly. The number, okay, if the prime number is a congruent to 1 mod 4, or it's a multiple of 4 plus 1, it appears with a plus. If it's a multiple of 4 minus 1, it appears with a minus. So yes, you write a few more. Okay. Now, we know from calculus that if we have two series and both of them converge, then the sum will be a convergent series.
Yes.
Also the difference.
Yes.
So for the same reason, if we take two series and both of them are divergent series, I don't know about the sum. It could be convergent or divergent. We don't know. But if I have a series that's convergent, a second series that's divergent, and we add these two series, then definitely the sum is divergent.
Yes.
Because if the sum was convergent, then you take the difference between the sum that's convergent and the one of them that was convergent, and you get the difference that's convergent contradicting this. So what I'm trying to say here is that we write one more line, our series from last time, everything with plus, 1 over 3 plus 1 over 5 plus 1 over 7. So now just all the odd.
Oh, okay.
Yes, so we write everything with plus, and this is divergent. So now when we add these two series, we get a divergent series. So let's add. And when you add, right. But what happens? Excuse me, just a second. When you add these two series, minus 1 over 3 cancels.
Yes.
So let's remove minus 1 over 3.
Yes. I am writing this other series.
Oh, okay, good. So let's add the two series and divide by 2.
Okay.
So in other words, 1 over 3 minus 1 over 3 is 0, but then 1 over 5 plus 1 over 5 is 2 over 5. We divide by 2, so it's 1 over 5. Okay, so let's, yes, so the sum divided by 2 is equal. Let's now ignore the zeros and just put those numbers that are not 0. So remove the zeros. I mean, you can keep the zeros here, but okay, you can keep the zeros. But which one is appears with a plus? 1 over 13 plus.
All the mod 4.
All right. And the next prime that's congruent to 1 mod 4 is 19? No, 17.
Yes. 17, sorry.
Plus 1 over 17. 1
yes.
over 17 plus that. And we know that the sum is divergent. So we say this diverges, or if you want to say the sum is infinite, because it's the sum of positive numbers.
Yes.
Okay, but for this sum to be divergent, that's a consequence of this, is that we have infinitely many primes that are congruent to 1 mod 4. And that's Dirichlets proof. So there must be infinitely many primes that are congruent to 1 modulo 4. To make the sum. Now, Dirichlet wanted to show, and we stated his result in our class, right? For an arithmetic provision. In particular, for primes congruent to 3 mod 4. But how do you get that? You subtract the two series instead of adding the two series, so you subtract them. So 1 over 3 plus 1 over 5 plus which is divergent, and you subtract the one that's convergent. And we get one that's divergent.
Yes.
But when you subtract them, then 1 over 3 won't cancel anymore, but 1 over 5 will.
Yes.
So we are left exactly with those other terms that canceled before.
Yes.
So, okay, what do we get?
So then we only get the primes that are 3 mod 4.
Yes. So let's put a few of them there and say that the sum is divergent. And that's a proof for us that, okay, There are infinitely many prime numbers that are congruent to 3 mod 4 also. Before we end this video, just wanted to take just a few more minutes and say something about what he did in general. If you work modulo, if you work with an arithmetic progression of this form, numbers congruent to 3 mod 4, they form an arithmetic progression. 3 plus 4 is 7, 7 plus 4 is 11, 11 plus 4 is 15, and so on. 15 is not a prime, but it's in this arithmetic progression.
Yes.
Infinite arithmetic progression, and his theorem was that in this infinite arithmetic progression, there are infinitely many prime numbers.
Yes.
So he wanted to do this for other arithmetic progressions, as we stated in class without proof. Well, we'll prove this again, as I said in class 1 class, in more generality. But for us right now, just to see his next idea, you see, if you only take two series and you just add and subtract, you only get two congruence classes. It was enough modulo 4 because all the primes that are, except for prime number 2, all the primes are either congruent to 1 mod 4 or congruent to 3 mod 4.
3 mod 4.
But suppose
8.
Suppose you want mod 8 or mod 10.
10, yes.
Mod 10. Now, mod 10, there are 4 arithmetic progressions that can have, in principle, infinitely many primes. Those 1 mod 10 numbers are relatively prime with 10. 1 mod 10, 3 mod 10, 7 modulo 10, and 9 modulo 10. So, as you wrote, 10n plus 1, not 10n plus 5, but 10 plus 1 plus 3 plus 7 and plus 9. 10n plus.
Sorry. Yes.
So 1, 3.
11. Okay, so that's the same.
11 is like 1. So yes. And plus 9. Yes. And he showed, you see, that in each of these arithmetic progressions,
yes,
in each of these arithmetic progressions, there are many primes. Similarly, if you take modulo 5, let's say 5k or 5n, 5n plus 1, 5n plus 2, 5n plus 3. Let's write the 4, yes, all, because now all these congruence classes are relatively prime with 5, 5n plus 1, 5n plus 2, plus 3, and plus 4. Okay, so he showed that in each of them, each of these arithmetic progression, there are infinitely many primes. But what I'm trying to say is that for him to be able to do this, he needed more L functions. That's how these functions are called, this L of S. Just 2 of them won't do the job, like Riemann Zeta-Function was needed, and another one. So he introduced more such functions. And one such function, I'll write, let's call this, use another letter, any letter you want, capital letter that you want. R of S equals 1 minus 1 over 2 to the S minus 1 over 3 to the S plus 1 over 4 to the S. Then 5 is ignored. In the same way we ignored multiples of 2 when we created our first L of S, we're going to ignore multiples of 5. So we go directly to 6. And again, we keep this periodicity. If we, yes, modulo 5. So 6 is congruent to 1. We put a 1, so we put 6 with plus. 7 is congruent to 3. No, 6, what am I saying? 7 is congruent to 2. We took 2 to the S with a minus in front of it. We'll take 7 to the S with a minus. So exactly as you wrote, 1 over 9 to the S. Then we jump over 10. And we go with 11. Again with plus. And so on. So if I just look at the coefficients, people call them Dirichlet coefficients, let's write another line. Coefficients are one minus one, or this signs plus minuses, huh? 1 minus 1 minus 1 plus 1, then the next one is 0 because it's ignored, the multiple of 5, and then again it repeats 1 minus 1 minus 1 1 0 1 minus 1. Okay, so last idea, have we seen these things before? Yes, we did, but let's see if we can recognize this.
1 minus 1 minus 1 0 1 minus 1 minus 1.
Okay, can you tell me which numbers? Yeah. Oh, yes.
Something to do with Mobius function by any chance?
Oh, not with Mobius, but we're close. With quadratic residues and quadratic non-residues.
Oh, okay.
This is exactly the Legendre symbol.
Legendre symbol. Okay.
It is exactly Legendre symbol. So he's using the Legendre symbol to construct functions and other similar things. In other words, let's see.
So 2 and 3 are
2 and 3 are quadratic non-residues mod 5.
Oh.
4, that's why we have a minus there. Legendre symbol modulo 5. Yes. 1 appears with plus. 1 is a quadratic residue. So the quadratic residues mod 5, if you think about those, we can find quickly. We just look at squares. What are the squares? Mod 5, right?
Yes.
1 square, 2 square, 3 square, and 4 square. But what are these numbers? 9. Yeah, but 9 mod 5 is still 4. 3 square is 9.
That's it.
Or I mean, 1, 2, 3, 4. 4 square is 16. Modulo or minus 15 is 1. Right. And then it's 0 because it's a multiple of 5. And they continue in the same way, as we know. So these are the squares. And that's exactly the coefficients. Oh, just a second. Exactly the coefficient. The Legendre symbol. So these are exactly the quadratic residues, 1 and 4. That's why the coefficient of 4, it's plus 1. But the coefficient of 2 and the coefficient of 3 are minus 1 in our series because both of them are quadratic non-residues. So if the number is a quadratic non-residue, we put a minus in front. If it's a quadratic residue, we put a plus. So you have minus 1 over 7 to the s because 7 is a quadratic non-residue mod 5. 7 is a quadratic non-residue because 7 is congruent to 2. 2 is a quadratic non-residue.
Yes.
The only quadratic residues are 1 and 4, as you can see. And again, you see, if you look at what happens at, so this will work again. And the fact that this arithmetic function, if you think about that, it's just the Legendre symbol itself. You use it as coefficients for our L function, our 1 minus 1 minus 1, 1, 0 in this case, and so on, is multiplicative. That's one thing we prove when we use those two colors, green and red.
Yes.
The fact that that is multiplicative helps actually in this context to show that this L function has an Euler product. And then we can take logarithms and proceed in the same way. So it was essential for us. In fact, it needed to have an Euler, it needed to be multiplicative in order for it to have an Euler product. So again, again we have Euler product. Again we have sum of inverses of primes. But in this case, what kind of sum we have with these coefficients? Because we have we will have a 1 over 2. I'm thinking about what will be the analog of our sum. There was 1 minus 3 minus 1 over 5 plus 1 over 7, whatever. In this case, it depends on the coefficient. So, so after, again, a long story made short, we will get the following series. 1 over 2, this time we do have a 1 over 2 because 1 over 2 to the s is part of the series. Okay,
Yes.
1 over 2, but we don't have a 1 over 5. There are no multiples of 5 in there.
Yes.
So 1 over 2 is with minus because it was a non-residue. Minus 1 over 2, and then minus 1 over 3. It appears with minus.
Minus 1 over 7.
Oh, we cannot have everything with minus.
Plus 1 over 11.
Uh-huh. And so on and so on and so on. We can write it as a series without commas now in between them as a series. And now let's establish one last thing for this series. Is this convergent or divergent? We know how to find this answer. It's convergent because we can look at what happens with our L function where s approaches 1, because the same thing will happen with the logarithm. So we take logarithms in order to get to the primes. But in order to see if this goes to infinity, we just look at the initial function. And what happens when you take s to be 1 in here, in the initial definition of the function? Is this infinite or not? We get the following. R of 1, just R of 1, is well defined. It's like L of 1 was well defined. L of 1, we found that it was pi over 4. Is well defined. The series is convergent. But what is the series? Let's just see why this series is convergent. Let's write it as a series. R of 1. We have to go back to R of s and take s equals 1 in the definition. Where is R of s? Yes, if we think about take s equals 1, can put it here. It's just take s equals 1. So we replace 1 over 2 to the s by 1 over 2. So then we get 1 minus 1 over 2 minus 1 over 3 plus 1 over 4, and then plus 1 over 6 minus 1 over 7. Yes, it's not about primes. All numbers are, except multiples of 5. So the coefficients you recall, 1 minus 1 minus 1, 1, 1 minus 1 minus 1, 1, and so on. Now you see, this looks like an alternating series, so it has a good chance to being convergent. But how can we actually show that it's convergent? You see, we can write this as a sum or a difference of two convergent series. I can do the following. Take sum of it. 1 minus 1 over 2 minus 1 over 2. Then jump over the next two and then go to plus 1 over 6 minus 1 over 7. Then again jump over the next two and we go to the next number that's congruent to 6, modulo 5. 1 over 10 is going to be missing as a multiple of 5, but 1 over 11 minus 1 over 12. Now this converges. This is a clean
subset of the alternating series.
Yeah, some of them are with minus, some with plus. Right, and this is an alternating series that's convergent.
Yes.
And the other part, we jumped over. Let's have a look at it. It's minus 1 over 3 plus 1 over 4 minus 1 over 8 plus 1 over 9. So numbers congruent to 3, numbers congruent to 4. One is with plus, one is with minus. So this is convergent. Again, it's an alternating series. But in some sense, we got lucky because we had as many pluses as minuses. So we were able to combine them in alternating series. But isn't this true in general?
Yes.
It's something we proved that for any prime number, for instance, prime number, instead of 5, one does this module, there are exactly as many quadratic residues as quadratic non-residues. So again, that's a place where this is used. So you can arrange a plus with a minus, and arrange this to be an alternating series and convergence, and show that it's a convergent series. So this will say, for instance, that this sum is convergent. That's the first line on. The first line on this page. Yes, because that's about primes. But those primes that are congruent to 1 mod 5 and
Can
4
show
mod 5 are
subtraction.
added. Those that are 2 mod 5 and 3 mod 5 are subtracting. And
Yes.
this is convergent. So he found several of these things and then combine again with the Riemann zeta function, because that's the one for which we know that the sum is divergent.
Yes.
When you take all of them with plus. So
Yes.
by this kind of combinations, he was able to obtain all the arithmetic progressions in more general. So that's the general idea, and I think we can stop this video.